This video is going to go over nuclear chemistry, which is sometimes a Chem 101 topic and sometimes it's a Chem 102 topic. It just varies. Nuclear chemistry is a little bit different than the chemical reactions we're going to be talking about the rest of the semester and into next semester. So here we tend to treat nuclear chemistry as an early topic, and it's very separated and different from the other chemical reactions we're going to talk about. So most chemical reactions involve changes in the electrons on the outside of the atom, valence electrons. In the case of nuclear chemistry, we're actually changing the nucleus, which is why it's called nuclear chemistry. And this borders on some physics topics as well. There's a lot of overlap here with physics. So we're going to start by talking about radioactivity. Radioactivity is when a nucleus is unstable and what we say is it decays or radioactively decays, which means that its nucleons, right, the protons or the neutrons, they change and it converts the element into a different element by changing the nucleus. So there are different kinds of radioactivity. The shown here are sort of two of the more common types. One is alpha decay. So there's a picture here of an atom of a plutonium-240 atom undergoing alpha decay to form uranium-236. And then that comes along with the ejection of what's called an alpha particle, which we're going to talk about. And then at the bottom is a beta decay, which shows carbon-14. So carbon-14 dating is related to this process. So carbon-14 will change into nitrogen-14 and at the same time emit a beta particle, which is an electron. So we're going to start, these are just sort of an intro idea behind radioactivity. So we're basically changing the identity of the element by changing the nucleus. And then along with this radioactivity, this radioactive decay becomes radiation that comes out of it, right? And so that's also important. So we're going to talk about that. So there are different kinds of radioactive decay, and we're going to talk about all of them. One is alpha decay, one is beta decay, one is positron emission, and one is electron capture. And we're going to talk about how this changes the nucleus of the atom. And then along with the radioactive decay comes radiation that is emitted during the decay process. So there are different types of radiation, and this is the kind of radiation that you sometimes are worried about. You know, radioactive decay, like you know, the fallout from hydrogen from bombs and nuclear meltdowns from power plants and things like that. So those types of significant catastrophes result in some significant health hazard due to radiation. So there are different kinds of radiation, and some we are more detrimental than others. Alpha radiation. There is also beta radiation. So alpha radiation comes from alpha decay. Beta radiation comes from beta decay. Gamma radiation comes from different kinds of radioactive decay, and this is the kind that you're most worried about. We'll talk about the different kinds and how they affect tissues. A little bit of biology in your otherwise chemistry and physics talk. We'll come back to the summary later as well. You can use it to, you know, to think about how to write these reactions, but we're going to that. So the different kinds of radiation have different sort of, we can categorize them as how easy they are to sort of stop. So for example, an alpha particle would be stopped by just a piece of paper. So if you had a decay source that was emitting alpha radiation, if you simply put a piece of paper between the radioactive source and you, it would never hit you because the alpha particle can't go through the paper. However, beta particles can go through paper, but they can't go through aluminum, and so aluminum would stop them. Gamma radiation is the most penetrating of all of them, and gamma radiation is a type of radiation. When you learn the electromagnetic spectrum, gamma is part of the electromagnetic spectrum. It's a type of wave. It's shorter than X-rays. It's more energetic than X-rays. They're the ones that we really worry about in terms of harming us. And so some kinds of gamma radiation can be stopped by lead and others can't be, and so that's the most penetrating and the most harmful to life. Now this is, so based on the particle that is emitted, it is affected differently in an electric field. So beta radiation is strongly deflected toward a positive electrode, implying that it is negatively charged. Gamma radiation is undeflected because it is not charged. Alpha radiation tends to be deflected toward a negative electrode, and so based on that, you would know that an alpha particle is positively charged. And so this is just a minor point on how these are affected, how you might determine which one is which, or how they studied some of them. Now, this is important. I want to talk about the different types of decay. And so this is an example of a nuclear reaction equation that shows you the reactant on the left. This is uranium-238. And the products of alpha decay. So one of the products of alpha decay is an alpha particle, which is just the nucleus of a helium atom. So sometimes the alpha particle is abbreviated alpha with that Greek symbol alpha, with that funny squiggly A, or sometimes we just write it as a helium because that's what it is. And so helium has 2 protons and 2 neutrons, which means it has 4 nucleons total, which means it has a mass number of 4. And so we write that to the right. You'll notice there's not charges here. These are just the nuclei. And if it loses 2 protons and 2 neutrons, then that means that the uranium-238 is going to, its atomic number of 92 is going to change from 92 to 90 because it loses 2 protons as part of that alpha particle. Now, since it loses 2 neutrons, it also goes down by 4 in mass number, and so it goes from 238 to 234. And so whenever you do these alpha decay reactions, whatever you start with on the left is going to be given to you. So uranium-238 would have been given to you in the problem. And then the alpha particle is the helium with the mass number 4 and the atomic number 2. And then the other product you would just get by taking 4 away from 238 to give you 234, and you take 2 away from 92 to give you 90. And then you go to the periodic table and you look up what is element 90, and you would say, oh, it's thorium, and you would write down TH. Okay. Here, back to beta decay, the mass number does not change in beta decay, but the number of protons increases by 1. Positron emission is kind of the opposite. You emit a positron instead of an electron. And so a positron, so in this case it's sort of like you have a proton that gets converted into a neutron, and then a positron is emitted. Okay, so in this case the number of nucleons, or the mass number, still stays the same, but the number of protons goes down by 1. So you notice here potassium 40 goes from element 19 to an atomic number of 18, which is argon. But the mass number stays the same because you've simply converted a proton into a neutron, so you have the same number of total mass number, or nucleons. Positron emission is the positron emission is the PE in a PET scan. And so these are used to do imagery in order to identify in some types of cancer. So if you've heard of PET scans, then the PE in PET scan is positron emission tomography. Finally, electron capture has the same effect, but instead of having a positron emitted, you would capture an electron. And so sometimes an inner shell electron will be captured by the nucleus, in which case a proton that captures that electron will combine with the electron to form a neutron. And so you go from an atomic number of 80 in this case for mercury 197, you lose a proton, you go down to gold, and then but the mass number stays the same. And so for electron capture and positron emission, they have the same overall effect. And we're going to practice some of these to make sure everybody knows how to do it. But before we do that practice, I want to do one more thing, and that is this idea of the belt of stability. So the question is, why do some elements, some isotopes decay radioactively and others do not, others are stable? So if you plot, so this plot is called the belt of stability. So if you plot the number of neutrons, that's along Y, and the number of protons, that's along X here, then you'll see that the black boxes represent stable isotopes or stable nuclides. That's the nucleus of a stable isotope. So this black box is called, this black diagonal line is called the belt of stability. Now the diagonal there, the line that's drawn straight, that represents where the number of protons and the number of neutrons are the same. So what you discover is that with really small elements, the number of protons and neutrons tends to be equal. But as the atomic number goes up and you move along to the right on the x-axis, we're getting more and more protons. As we get more and more protons, we need even more neutrons than usual to sort of maintain a stable nucleus. And so that's why it doesn't lie along that diagonal line. The neutrons are sort of important to maintain the stability when you have a whole lot of those positive charges near each other, right? So the more protons we get, then the more and more and more and more neutrons we need to maintain a stable nucleus. So what you also see in here, these boxes, right, represent different kinds of decay processes that are observed for these particular unstable isotopes, right? So the yellow box is sort of at the very top, way above the black belt of stability. These boxes are nuclei that undergo alpha decay, which causes a reduction in both the atomic number, Z, and the mass number, which is A, right? And so that's going to cause them to sort of come back down toward the black diagonal line. These aquamarine boxes undergo beta decay, and in that case what happens is a neutron gets converted into a proton, remember, right? And so if that's true, that's going to push these aquamarine boxes closer to the black belt of stability, right? These orange boxes either undergo positron emission or electron capture, but for either one the result is the same. They end up converting a proton into a neutron, which is going to push them up higher, closer to the belt of stability. And we're going to do these practice problems to make sure everybody knows how to do them. We'll do those next. Okay, so we have this practice problem. We're going to write a few balanced nuclear equations. Part A, ruthenium 106. That's a specific isotope of ruthenium, and the symbol is given there with the mass number in the upper left. And then the symbol, and it undergoes beta decay. So the first thing we're going to do is write down the symbol for ruthenium 106, which is given. Next we have to include the atomic number. Now, I know in class we talked about the fact that the atomic number and the element symbol, writing both of them is a little bit redundant, so you don't typically do that. But for nuclear equations, it's a good idea. It's not only a good idea, but you should definitely do it in this class. And so even though ruthenium has a specific atomic number, you need to include it here so that you can better write the equations. So we're going to go to the periodic table and find ruthenium, which is here. It's element 44, right? And then we're going to go back and write a 44 in the lower left-hand corner. And then we do our arrow. It undergoes beta decay, which means a beta particle is one of the products. A beta particle is an electron. There's a 0 in the upper left-hand corner because it doesn't have any nuclides, and so it doesn't contribute to the mass number at all. It basically is almost massless. And then the -1 in the lower left-hand corner is sort of related to the charge, but it's in the atomic number area. So if you remember, beta decay occurs when a neutron is converted into a proton, and then there's an electron left over, a beta particle, and that needs to be ejected, right? So that is what is emitted. That's the beta particle that comes out. And so if we have a neutron converted into a proton, that means that the number of protons must go up. So that's going to go up to 45. And that's what I write here. Neutron gets converted into a proton and we eject an electron. So that means that the atomic number goes up by 1 because we have a new proton that wasn't there before. The mass number stays the same because we have one nuclide, the neutron, that gets converted into a proton. So the total mass number is still 106. And then we need to go and see what element that is. That's rhodium. So we write RH there, and that is the finished nuclear reaction. Next, we're going to do alpha emission of fermium-247. We're going to write the symbol for that with the 247 in the upper left corner. And then we're going to look up the atomic number on the periodic table. Fermium is down here, so number 100. And then alpha decay, that means an alpha particle is one of the products. And that is, remember, a helium nucleus. And so you have 2 protons and 2 neutrons. So you have 4 nuclides altogether. So the mass number is 4 in the upper left-hand corner. And then its atomic number 2, it has 2 protons. So that means that the atomic number 100 is going to go down by 2 because you lose an alpha particle which has 2 protons, and so that's going to go to 98. And then the mass number 247 is going to go down by 4 because you lose 2 protons and 2 neutrons, so that goes down to 233. So remember that the sum, here we're just looking up the atomic number. Sorry, that was somebody calling to sell me something. Anyway, so remember that the numbers, the superscripts over here, 243 and 4, those need to add up on the right-hand side to whatever it is on the left-hand side. So 243 and 4 plus should add up to 247. 98 and 2 adds up to 100. So you can use that to verify the answer. We looked up in the periodic table that element 98 is californium. So this is the finished nuclear reaction. Next, we're going to have electron capture by polonium-204. Polonium-204, this is the symbol. Next, we're going to write the atomic number. We're going to go to the periodic table and write the atomic number for polonium. Polonium is here, number 84. So we go back and write 84. Electron capture means that an electron is a reactant in this reaction. And so electron capture is when the nucleus captures an inner core electron. Okay, so one thing you can do is, just like I mentioned before, this 204 plus 0 should equal what's on the right, 204. 84 minus 1 has to equal what's on the right, which is 83. So one way to do this is to just know that an electron is a reactant. And remember, you have to remember the symbol for an electron, that there's a 0 in the upper left-hand corner, and that there's a -1 in the lower left-hand corner. And that's related, remember, to the charge, but it also relates to sort of the number of protons, because remember, a proton and an electron sort of combine to make a neutron in the nucleus. And so another way to do this is to say, okay, electron capture is, if you look over here, this is when one of these inner core electrons is captured by the nucleus. And so if a neutron is a proton and an electron, that means that when the nucleus captures an electron, it must combine with a proton to make a neutron, right? So that's going to combine with the proton, and we're going to make a new neutron. So that means the number of protons is going to go down by 1, which it does. The number of neutrons goes up by 1, but because the one nuclide converts into the other, the mass number stays the same, 204. So protons goes down by 1, neutrons goes up by 1, the mass number stays the same. Bismuth is number 83, so this is the finished nuclear reaction here. The last one, now I'm circling it just so you know what is the actual answer here. I've got a whole bunch of extra stuff on here. Barium-125, we're going to write that symbol. We're going to look up its atomic number. Barium is a alkaline earth metal, number 56. Now, the result of on the nucleus of electron capture and positron emission are the same. Okay, so you end up, the end result is for both of them that the mass number stays the same. So this is going to stay 125. And the atomic number 56 will go down by 1, so it'll go to 55. So these have the same result on the nucleus, or on the resulting isotope. But instead of capturing a proton, it emits a positron, which is like an electron that's positively charged. Okay, so with a positron emission, what happens is a proton converts into a neutron, and it has that extra, almost massless, positively charged particle that it must eject, and that's called a positron, and that's usually got this abbreviation with a beta with a plus, or it has an E just like the electron, but it's a +1 in the lower left-hand corner instead of -1. So if we write that symbol here, and remember that these should add up on the right-hand side, 0 plus 125 equals 125, 1 plus 55 equals 56. But the same is true here. We know that we're converting a proton into a neutron, so the number of protons goes down by 1, the number of neutrons goes up by 1, so the total mass number stays the same. We need to look up element 55, which is going to be an alkali metal. That's cesium. And this is the final answer. So here I've erased everything so that you can see the actual answers. I erased all the extra nonsense around everything. So next we're going to move on to the next question, which is here. Consider the diagram to the left, which shows a radioactive decay process. The arrow points from the initial isotope to the decay product. What type of decay processes are depicted? So we need to look at the atomic number is along the x-axis. That's the number of protons. The number of neutrons is along the y-axis. So we're going to write that down. We're starting initially with 69 protons and 79 neutrons. Okay, make sure that you can read that graph well. Okay, and then the final situation is that we have an atomic number, 68 protons and 80 neutrons. We can add those together to get the mass number, which is 148 for both of them. So now we need to figure out what this could be. Okay, so there are 4 types of emission processes. If we go through the 4 different types, we can compare them. Is this alpha decay? Alpha decay would result in the mass number decreasing by 4 and the atomic number decreasing by 2, because remember, an alpha particle is a helium nucleus. And that is not what's happening here, right? The mass number stays the same and the atomic number is going down by 1. So that's not true, no. Is it beta decay? Beta decay has a neutron being converted into a proton and it ejects a beta particle or an electron. And if this were the case, then what would be happening is the atomic number would go up by 1 and the mass number would stay the same. That is not what's happening because the atomic number is going down by 1, so this can't be the answer either. The other 2 possibilities are positron emission. So for positron emission, the proton gets converted into a neutron and ejects a positron. In this case, the number of protons would go down by 1, but the mass number would stay the same. Now this is a possibility because this is what's happening. So this is a check. Yes, that could be true. But there's still another possibility, and that is electron capture. Remember, electron capture has the same effect on the nucleus as positron emission. So in this case, a proton combines with an electron from the inner core and converts it into a neutron. And that is going to have the same effect. That's what this is. This is an arrow pointing to this where the effect is the same as it is in positron emission. And so this is also a possibility. And so that means that the answer is either electron capture or positron emission. That's what this says up here as my answer. Now part B, we're going to move on. Identify by name and symbol both the final isotope and both the initial isotope and the final isotope. So I'm going to erase this down here. And if we know that the atomic number is 69, then we can look up what that is. I'm going to put that in the lower left-hand corner, and I'm going to look up element 69, which is over here. I'm going to write the symbol Tm. And then mass number is 148. I'm going to write that in the upper left-hand corner. That's the initial isotope. The final isotope has an atomic number of 68. So we'll write that in the lower left corner. We'll look up what that is. That's just to the left here, erbium. We'll write that symbol, and we're going to write the mass number in the upper left-hand corner. And that is the final isotope, and we'll circle that. So that's the answer to the second part B. Moving on to number 3, consider the diagram to the right, which shows a series of radioactive decays in which the radioactive isotope A decays ultimately to the stable isotope E with intermediate unstable / radioactive isotopes B, C, and D. So this is actually pretty common for a decay series to occur, where the first isotope A is unstable, decays to B, which is also unstable, decays to C, which is also unstable, and it will continue to decay until it gets to a stable isotope, which in this case is E. And so these series of decays are pretty common. So I've listed A, B, C, and D, C, D, and E here so that we could look at each one, because we need to really figure out what's happening here. Now I can tell you right off the bat, what type of decay. When you look at these shorter arrows, you know, one thing you can do is see that A going to B and D going to E are kind of the same sort of process. We're going from 147 neutrons to 146. So the number of neutrons is going down by 1. The number of protons is going up by 1. So I can already tell you that this appears to be beta decay because the number of protons goes up and the number of neutrons goes down, which means that a neutron must be converting into a proton and then ejecting an electron, which is a beta particle. So I can kind of tell from looking at it, but if you can't tell from looking at it, you just have to write down what's happening, okay? So we'll write down what's happening, but I think you can see that A going to B is the same as D going to E. It's the same type of decay. That's also true for B to C and C to D. This is a really long arrow, right? And so these long arrows indicate that it's losing more than one proton, right? It appears to be losing 2 protons at a time, and it also appears to be losing two neutrons at a time. So this must be alpha decay because that's the only one that causes a change by more than one nuclide. So, but let's write them all down just to be sure that everybody understands. So for A, if we look at what's happening, A has 94 protons and A has 147 neutrons. If we add those together, we get a mass number of 241. We can do the same thing for B. B has 95 protons and 146 neutrons. C has 93 protons and 144 neutrons. And down here, I'm just adding them up to figure out the mass number because that's an important part of the symbol, which is what we're going to do in part C. And then in part D, let's see, isotope D has 91 protons and 142 neutrons. You add those up, you get 233. E has 92 protons and 141 neutrons, which you can add together and get 233. So now when you see what's happening, we can see we're trying to figure out A going to B, this is to answer part A, and D going to E. This is the question. What type of decay processes are represented by the shorter arrows, A to B and D to E? So I circled those here so that we can really look at them more carefully. So we're going from 94 to 95 protons. So the number of protons is going up by 1. The number of neutrons is going down by 1. So it looks like we have a neutron being converted into a proton, which is definitely beta emission, right? So the atomic number goes up by 1, the mass number stays the same. That's also true here. We have 91 protons going to 92 and 142 neutrons going to 141. So a neutron must have converted into a proton. So that is beta emission. Remember, a neutron is the same as a proton and an electron. So if a neutron converts into a proton, that means that it has to eject the electron, right? That's still a part of the process. It just gets kicked out of the nucleus. So protons goes up by 1, mass number stays the same. That must be beta emission or beta decay. Those are synonyms. Part B, we're going to look at what type of decay process are represented by the longer arrows, B to C and C to D. So if we look at those two, we have protons going down by 2 from B to C, 93 to 95 to 93, and also from C to D, 93 to 91. So the atomic number goes down by 2. And the mass number is going down by 4, right? 241 to 237, and then 237 down to 233. That has to be an alpha particle, right? So that's the only decay process. Alpha decay is the only one that results in that large of a change in the atomic number and the mass number at one time. Now, part C says identify by name and symbol the isotopes A through E. So we're going to write down the symbols. So for A, we have 94 protons, and mass number is 241. Now I'm going to tell you right now that the mistake you're going to make is you're going to write 147 neutrons, right? Because that's what's on the graph, right? So it's a very common mistake. You accidentally write 147, but remember that what's in the upper left-hand corner is the total number of nuclides. It's the mass number. So you have to add those two together. 241. Element 94 we need to look up because I can't remember what it is. There it is, plutonium, Pu. Pu. It smells bad. And then the next one, we're going to write the mass number in the upper left-hand corner, element 95. We're going to look up on the table. Element 95 appears to be americium. I'm going to write that one down. And then 93, and we add those up, and 237 is the mass number, neptunium. And then D has 91 protons and 233 nuclides. That's, what is that, PA? I don't even remember what that one is. 233, element 92, I know this one. This one's uranium. 92 is here. It's one of the only ones I remember from the actinide series. And so this is the final answer for isotopes A through E. Okay, so let me know if you have any questions about that.